Hello and welcome to this vignette on odds ratios. Before we jump right in, we'll do a quick review of some basic probability principles that I think will be helpful to understanding the definition of odds ratios. So this Venn diagram represents the event space for two events, A and B. It covers every possible outcome. We can have A or B, or both A and B, or neither A nor B. So here's where we have A, here's the space where we would observe B, this is where we observe neither, and this is the intersection where we see both A and B. Let's go ahead and add some numbers that represent the probability of observing these different outcomes. So let's say that on average, out of every 100 trials, A happens without B 23 times. B happens without A 12 times. A and B both happen 6 times, leaving 59 trials where neither A nor B occurred. So the probability of observing event A is 23 plus 6 over 100. We have 23 and 6, that makes up A. Divide by the total number of events observed, and that gives us a probability of 0.29. Likewise, the probability of observing event B is 12 plus 6 over 100, or 0.18, 18%. Likewise, the probability of observing A or B, or both, including the possibility of both events, the probability would be 23 plus 6 plus 12 over 100, which is 0.41. And the probability of observing both A and B is 6 over 100, which is 0.06. Now, conditional probability is very similar. Oh, we got that slide twice. All right, conditional probability is very similar. If we want to calculate the probability of A given that B happened, that is, we know that B occurred, what is the probability that A also occurred? This is 6 over 12, or 6 over 18, sorry. Which is 0.33. We divide by 18 because we know that B occurred. And so there are 6 plus 12 trials, or 18 trials, where B occurred. And so out of those 18 trials where B happens, we will observe A in 6 of them, or about a third of the time. This is equal to the probability that both A and B occur divided by the probability that B occurred. And this formula is often called Bayes' rule. So probability of A given B is equal to the probability of A and B, or the intersection of A and B, divided by the probability of B. Now let's go ahead and define the odds of an outcome D given an exposure E. We usually think of this in terms of the odds of disease given an exposure. If we fill this table with all of our observations, we have N11 individuals that were exposed and had disease. We have N10 individuals who were exposed and did not have the disease. We have N01 individuals who were not exposed and had the disease. N00 individuals who were not exposed and did not have the disease. These row totals here and one dot are all of the individuals who were exposed, and 0 dot are all of the individuals that were not exposed. N dot 1 is all of the individuals who had the disease. N dot 0 is all of the individuals who did not have the disease. So these had the disease, these did not have the disease. for a total of big N samples. So, now that we have this information, we want to use it to calculate a measure of the likelihood of developing the disease D given the individual was exposed to E. First, we'll calculate the probability of disease given exposure and the probability of no disease given the exposure. We'll apply Bayes' rule here. So these conditional probabilities are equal to the probability of disease or no disease given they were exposed divided by the probability that they were exposed. So we can use this table up here to calculate these probabilities. That's simply N11, that is the intersection where they were exposed and had the disease, divided by N, big N, that turns it into a probability, divided by N1 dot, which is the probability that they were exposed over big N. That gives us the probability that they were exposed. These big N's cancel and we get N1, 1 divided by N1 dot. That's the probability of disease given the exposure. Same thing with no disease given exposure. We have the intersection divided by the probability of exposure, N1, 0, which is where they were exposed and had no disease, divided by N1 dot, which is the number that were exposed. The big N's cancel and we get this value here. So now we can calculate the odds of disease given the exposure. This is the ratio of the probability of disease given exposure to the probability of no disease given the exposure. That's a mouthful. So we divide the probability of disease given exposure by the probability of no disease given exposure. That's also the probability of disease given exposure divided by 1 minus the probability of disease given exposure. But we'll calculate it this way because we have all of those numbers up here. So probability of disease given exposure is N11 over N1 dot. Probability of no disease given exposure, we just calculated that, is N10 over N1 dot. N1 dot cancels and we get the odds of disease given exposure are equal to N11 divided by N10. So if the odds of D given E were equal to 2, then given that the individual was exposed to E, the exposure, the probability of developing disease D is twice as high as not getting the disease when they were exposed. If the odds of D given E are equal to 1/2, then the opposite would be true. Given that the individual is exposed to E, the probability of developing disease D is half as much as not getting the disease. Or in other words, given that an individual is exposed to E, the probability of not developing D is twice as high as the probability that they do get the disease. Now this is an interesting measure, but it doesn't tell us the whole story. For example, let's say that given the fact that I have brown hair, the odds that I will get HIV if I share a needle with an HIV positive person is 0.02. That's a pretty low number, so that means I'm not likely to get HIV after using one dirty needle. What does that have to do with my hair color, though? If you've guessed that it has nothing to do with my hair color, you would be correct, and that's what we would intuitively expect. That is why we prefer to talk to things talk about things in terms of odds ratios, because the real measure of interest is not the odds of getting disease given exposure, but the ratio of the odds of disease given the exposure compared to the odds of the disease if the exposure is absent. Put another way, I may be 50 times less likely to get HIV after using a dirty needle if I have brown hair, but I'm also 50 times less likely to get HIV after using a dirty needle if I have red hair. So thus our odds ratio would be 0.02 divided by 0.02, which is 1. In other words, my exposure to hair color is not going to change my risk of HIV acquisition. So in order to move to odds ratios, we need to calculate the odds of disease given the absence of exposure. So this is nearly the identical calculation that we just did. So feel free to pause the video if you want to look at these equations more carefully. But we'll just move on from here. So we need the probability of yes. So go ahead and work through this if you want to. Then we calculate the odds. Again, this is very similar. It's going to end up being N01 divided by N00. And feel free to pause the video and look at this more carefully if you want to do that. So now we can calculate an odds ratio. We have the probability or the odds of disease given exposure and the odds of disease given the absence of an exposure. We can divide those values that we just calculated, those odds, and we get N11 times N00, those two times these two, N01 times N10. So this will give us a more complete measure of what our risk of disease is when we're exposed compared to our risk of disease when we are unexposed. Put another way, the odds of disease given exposure gives us a measure of how likely we are to have disease after we are exposed. But the odds ratio gives us a measure of disease risk comparing exposed to unexposed individuals. So this isn't exactly how we're going to use it. This is sometimes referred to as a counterfactual group. So in real life, we observe an exposure or we don't. My hair is either brown or it isn't. There isn't really a way to measure what would have happened if I had red hair, but everything else was exactly the same. But we can imagine that there's some alternate universe where I decided to dye my hair red this morning, or maybe I was born with red hair, and went through my day exactly the same way. Did that change in hair color change my risk of HIV acquisition? In principle, there are much easier ways to measure differing exposures than going back in time and changing the exposure to see what will happen. When we design our study, for example, we can randomly assign exposures to different groups, or we can select controls who are as similar as possible to our cases, except that the controls don't have the disease. From these studies, we can calculate odds ratios, which then give us a better idea of what exposures we should focus on in our research or in future public health interventions. So back to defining odds ratios. The odds ratio for an effect, for an exposure E on a disease D, is the ratio of the odds we just calculated. Again, we divide these two values, and this is our formula. And that is our odds ratio. When we calculate the odds ratio for our HIV acquisition example, we get an odds ratio of 1, which tells us that people with brown hair are no more or less likely to get HIV than people with any other color of hair, all things being equal. On the other hand, the exposure in this silly example that really matters is needle sharing. the odds ratio for the effect of needle sharing on HIV acquisition is about 28. So people who share needles for HIV drug use, or for IV drug use, are about 28 times more likely to get HIV than the average non-IV drug user. Just a little point of interest there. So as with other measures, a confidence interval gives us a much better idea of the statistical significance of our estimated odds ratio. It gives us a better idea of how variable our data are and how accurate our estimate is. If we have a very tight confidence interval around an odds ratio of 3, say between 2.5 and 3.7, then we have identified an exposure that we can confidently say has a strong effect on the outcome. If, however, we have an odds ratio of 3, but the confidence interval, so it's the same odds ratio, but the confidence interval ranges from 0.4 to 22, we're going to be less impressed. We need to collect more data before we'll believe that there is really an effect of the exposure on the outcome. To calculate a confidence interval, we need to know the standard error of our estimate. And because we're dealing with a ratio, we're going to need to calculate this on the log scale. So the log odds ratio is normally distributed, but the odds ratio isn't. This is the formula for the standard error of the log odds ratio. It's 1 over n11 plus 1 over n10 plus n over 1 over n01 plus n1 over n00. Yeah, just read it. Fairly simple formula. Now, let's use what we've learned and go through an example. So let's say that we are interested in measuring the effect of STIs on HIV acquisition. So does having an STI make it more likely that you will get HIV? I've made these numbers up off the top of my head, but having an STI does significantly increase your risk of getting HIV when you're exposed to it. So here is our table containing the results of our pretend study. Our odds ratio is 36 times 89 divided by 32 times 54, which is about 1.85. Our log odds ratio is the log of that, which is 0.617. The standard error for our odds ratio is 1 over 36 plus 1 over 54 plus 1 over 32 plus 1 over 89. You get those numbers from up here, which is about 0.298. So to calculate the confidence interval, we're calculating a 95% confidence interval, which is what people will assume you're doing unless you specify otherwise. To calculate our confidence interval, we take our estimate and add and subtract 1.96 times the standard error. And when we exponentiate, we get the confidence interval of 1.03 to 3.32. So here's our log odds ratio, plus or minus 1.96 times our standard error, which is 0.298, which gives us this on the log scale. We exponentiate, and our confidence interval for our odds ratio of 1.85 is 1.03 to 3.32. Somewhere in that range. So it would appear that our odds ratio of 1.85 is statistically significant, since 1 is not included in the confidence interval, just barely. And if you're looking at it on the log scale, you would see that 0 is not included in the confidence interval on the log scale. So I hope you have enjoyed this introduction to odds ratio. This video will be followed soon by another one introducing logistic regression, where we will model the log odds of a binary outcome in a generalized linear regression framework, or a GLM. Thanks.